there is a final coming. Now, for me, this is very scary because I have to write it, but might be equally scary for you because you have to take it. I can tell you what I think is worth knowing, in no sense guaranteeing that that's what will be on the exam. Just by, I looked at my slides a little bit, and I can just remind you some of them because there's lots of stuff that is covered in lots of little bits and examples. So we basically start with chapter 7. We have covered everything up to 6 by the midterm. So we start from the midterm. So one thing I think is worth knowing, so I'm really not doing this by what's worth expecting on the final, but what I think is worth knowing for the rest of your scientific or intellectual career is relaxation oscillators. They're clocks, but they model typically biological or chemical clocks, and they have this property. Nonlinearity shows up in the particle. The state of the system doesn't move with uniform velocity, but it speeds up and then it slows down and it speeds up. That's one signature of nonlinear physics. It's very, very different. And this kind of null-Klein analysis is very handy. So if you understand these kinds of plots that, you go slow, 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 and then you fall off and jump and you get caught and go slow, slow. That's a kind of good thing to know. The other thing that I liked in chapter 7 was these models where you could vary some parameters and use null-Kleins to see whether you have fixed points where they're attractive or repelling. So that's what I liked in chapter 7. In chapter 8, bifurcations are very important and necessary. I'm not a big fan of going through a long list of bifurcations because, there are different special cases, etc. And if you need to know a particular bifurcation, you will find it in literature or appropriate wiki. But few of them are very important. So the most important, in some sense, is the saddle node that you see very often. Importance being how likely you have to run into it. And saddle node, I think of kinds of intersections of unstable and stable manifolds typically. And if they don't intersect, what you notice is slowdown or bottleneck behavior. That's quite often seen in many different systems. Then, as always in bifurcation, there is a critical point which is very fragile, in which the same point is attractive from one side, repelling from the other one. That you see almost never, but then you see these pairs of repelling and attractive fixed points, and that you see very often. So I think it's worth to know. The other bifurcation that's very often seen and intuitively makes sense to us is that if you're pushing some systems and making it less and less stable, and you're in 2 or more dimensions, one very generic thing that happens is that one way it can become unstable is that as it goes through bifurcation, it spirals out. But because system is confined, it has to end up on an attractive limit cycle, at least close to bifurcation. That's called Hopf bifurcation, and it's seen in fluids, and seen in neurons, and seen in lots of dissipative systems. So that's a very useful bifurcation. It's almost competitive with saddle node. Saddle node is what you see most often, but Hopf happens next. Then One thing that's always easy to discuss are fixed points or equilibria, but also other invariant objects, in particular periodic orbits, can go unstable. And that was discussed as global bifurcation, meaning that because a periodic orbit goes all over the place, when it bifurcates every place globally. And it's easiest to understand in this kind of simple normal models where I have radial direction and angular direction. So it's related to Hall bifurcation. But basically, you have situations where you spiral in, you get caught between, inside, outside, or you have some equilibrium that may be still stable, maybe has gone unstable, depends on parameters, surrounded by a limit cycle. That's a common thing to happen. Another common thing to happen is that sometimes you have oscillatory instability. So you first perturb some system. That was seen, described it in describing experiments about period doubling in fluids. You have some rotational motion like convection, and then that has a frequency, how many times you roll around per unit time. And when that goes unstable, the roll itself starts buckling and oscillating. And that leaves motions which are quasi-periodic, which you describe in two frequency angular velocities here at the angles. And because this thing is a fluid, the roll itself senses the oscillation of its wiggles, and wiggles sense the rotational roll, so they get coupled. And there is lots of interesting physics, chemistry, biology of that type. So quasi-periodicity is good. And it's easiest to model by thinking of uncoupled oscillators coupling. And that naturally gives a description not in one period of limit cycle, but a two-dimensional surface which is periodic, in other words, a torus that you glue together from these motions. Now, whenever you have this kind of global recurrent motion, they're very powerful tool to use are Poincaré sections. They're beautiful because they reduce something that goes all over the place to point in a codimension one border or separation in a state space. And very often it's much easier to understand what's going on by looking at these intersections and how the points move and accumulate rather than running the whole system and looking at the whole systems. So that's a powerful tool. Another powerful tool we have learned about is that if you have a small neighborhood, you want to see what happens to the whole neighborhood, not necessarily just one point in the neighborhood. And that's conveniently described in linear order by matrices, which tell you that, for example, if you have two dimensions, if you perturb along the x direction, then time later, there will be a consequence of perturbing in the x direction, but also y direction will develop because of nonlinear coupling, etc. And that means you'll look at something that compares the original direction to the final directions, and the matrix does that. So Jacobian matrix is a powerful, very useful description, because for matrices, we know how to deal with them, we know how to look at their eigenvalues, eigenvectors, and they all have important meanings. this concept works not only in 2 and 3 dimensions, but it works in million dimensions if you're doing machine learning or doing fluid dynamics. So that's something you should know from this course forever, that you should always not only try to find solutions of nonlinear systems, but you also should investigate a linear stability, which is given by Jacobian matrix, its eigenvalues, eigenvectors. Then the life takes place not in 3 dimensions that you and I walk in, but in a state space in general, which is especially true when you think of fluids. Every little participant in dynamics has some degrees of freedom, and together they tend to create high-dimensional state spaces. And often it's useful, like in Lorentz and Russlea studies system, to understand what happens in at least 3 dimensions. That's modeled by Russlea and Lorentz. I'll show next picture. And if you apply Poincaré sections to these systems, then you start studying, one-dimensional unimodal maps or multimodal maps. Very useful stuff. So you should remember that. Next thing that will happen is in higher dimensions, there is much richer world of possible behaviors of dynamical systems. So beyond being fixed points, which you had in 1 dimension, or limit cycles we had 2 dimensions, you can get, toroid motion on a torus in 2-dimensional embedded surface embedded in 3 dimensions, like quasi-periodicity that we just mentioned. But most astoundingly, and it took a very long time to appreciate this, Lorentz was a person who made it accessible to everybody. 3 dimensions suffice to get maddeningly complicated behavior, which we call chaos or deterministic chaos. So it's good to have at least qualitative understanding what these systems in 3 and higher dimensions do. And you should remember the definition of the chaos. First you can run away. That's measured by logarithm of an eigenvalue, stability in that direction, a rate of how fast you run away. But in dynamical systems, you cannot escape because you cannot have infinite energy or something to run away, so you keep coming back. The number of ways of coming back, you can think of it if all the doors were open in Howie building and every room had multiple doors, at least 3 doors, you could choose different paths of how you go from room to room or etc. And each one would be distinct. We could list all possible ways to come there. So that number of these guys, if it grows exponentially, is allowing to explore the space longer and longer. That logarithm of the number in statistical mechanics is called entropy, and that's why this word is used. It's a rate of choices open to you per unit time in the evolution. And chaos is positive Lyapunov plus positive entropy. So that's, you should remember. It's good to know how Lorentz map works, because Lorentz system works because you have this flow, it jumps around and goes on forever, ever. But if you put a Poincaré section on it, Poincaré section reveals a very simple structure. You actually seem to be sitting on 2-dimensional surface, which is kind of buckled. So when you cut in this Poincaré section, you just see a line it's like a piece of paper. We cut the scissors. And that gives you lots of powerful insights in how to organize chaotic behavior, prove it. And also suggests that you don't actually have to solve differential equations to understand how chaos works. This is captured by the logistic map. An interesting thing that happened when you make logistic map higher and higher, the thing that generically happens is a period doubling and sequences of period doublings, which I don't expect you to know how to derive mineralization theory and Feigenbaum numbers, etc. But at least qualitatively, that the way you think of this is that if you look at iterates, so second iterate of a parabola, it's something that is quartic polynomial, so it has to go up, down, as quartic polynomials do. And you realize that the way this goes unstable is the same way as any detail of this quartic polynomial goes unstable, but rescaled in the window that you look at. So just at least understand qualitatively what renormalization means. It just means that dynamical systems where you look at detail of state space, you see the same structure as you've seen before. And you can encode this in so-called renormalization theory. There you change the scales of everything and also rescale parameters appropriately. In this case also, the stability is very easy to understand. For Jacobian matrix, if you repeat something, it's matrix time matrix, a little bit complicated. But if you do it for one-dimensional maps, you realize that when you're studying stability, you're just studying iterates of map, and their stability by chain rule is a product of local stabilities. So that gives you some intuition how stabilities work. You move through the state space. Here you're fast, here you're slow, because its laws are nonlinear. They weigh different regions differently. And stability also says that local rate of stretching or shrinking depends on where you are. But if you use this chain rule, what's called Lyapunov exponent, mean stability, average stretching, is really just an average of stretching at every little step of the thing. So that's what Lyapunov exponents measure, and that's what, when people tell you, Lyapunov positive, that means on average, neighbors are separating because their distance is growing exponentially. Then there is a part of the course which is kind of very easy in the beginning, called fractals, which has the advantage you can do everything by hand. Has a disadvantage that it's not really what you like to measure in nature, but there's some aspects I like. You should understand what contour set is. No matter what you do, you should understand what that is. You should understand that you can use dynamics like Bernoulli map, where you stretch something by factor 3 and you throw the middle out to create contour sets. So they're intrinsic to dynamical systems. And they are sometimes fat or thick. And this is understood by looking at dimensions. They might be hard to compute, but intuitively, you understand that you count basically the number of intervals and their size, and you try to take the limit. So that's something you want to know. Another thing that's very useful to understand how chaos happens is that if you think of volumes and state space as door and dynamics, stretching them and folding them, you understand that repetition of that process must give you this infinitely fine structure, which is nicely captured by so-called Smale horseshoe stretching and folding process. Now, if this is two-hand waving, you can just write a two-dimensional map of a plane itself, which is non-linear because it depends at least one variable being quadratic and not linear. And this model is very beautiful. It's very easy to study its stability, find its fixed point, etc. And to this very day, we do not know whether this model is chaotic or not. So that's, roughly what I think you should take and remember 1 or 2 years after this course is over. And of course, be able to deal with specific examples in this final. So that's a brief introduction to the end. If there are questions, ask me, otherwise I'll run away. Thank you for your patience. I like your, Shantanu, I like your whiteboard. That's good. Hi,
Thank
Lucas.
Thank you very much. It's a fun semester.
Bye.
Thank you, Professor.
Thanks for hanging in there.